All right, let's move on to section 2.5. And section 2.5 can simply be summarized by these 5 rules. These are 5 rules you should have learned in elementary calculus. So all the problems that you need to do only depend on these 5 rules. The rule of linearity: if u and v are functions, then a linear combination of u and v, taking the derivative, is a linear combination of the derivatives. Here a and b are constants. A and b are not functions, they're constants. So a could be 3, b could be 7, but the a and b are not functions of x. Only the u and v are functions of x. Product rule: here you have the product of 2 functions, take the derivative, uv prime plus vu prime. Reciprocal rule: the derivative of 1 over v is minus v derivative of v over v squared. Quotient rule: this complicated formula, I actually never remember the quotient rule. I just use the product rule and the reciprocal rule. We'll see how to do that in a minute. And power rule is kind of an extension of the product rule. If you applied the product rule several times, you would get this rule. Now let's go back and look at his discussion. I think especially his discussion of product rule is very interesting because it shows where it comes from. This is a good picture to see. All right, let's look at this picture here. Here we have a rectangle. The x length here of this white rectangle is u of x. The y length is v of x. The product is u of x times v of x. Now suppose we change u a little bit, increase u a little bit, and suppose we increase v a little bit here. Then how does the area change? Well, you get these heavily shaded rectangles, and you get this lightly shaded rectangle. Now this lightly shaded rectangle is much, much, much smaller than the other 2 rectangles, so you can actually ignore the contribution of this tiny rectangle and focus on these 2 rectangles. Now if this here is delta u, then this rectangle here has height v and width delta u, so we have v delta u. Here we have delta v, the height delta v and the width u, so this is u delta v. That should be a little bit familiar with the product rule. In this case, my u delta, sorry, let me say that again. In this case, my delta u is the change in u when I change x to x plus h. My delta v is the change in v when I change x to x plus h. So in fact, delta u is u of x plus h minus u of x. Delta v is v of x plus h minus v of x. Okay, and then you can see that down here. Right? Here we have the total area, which is the difference between, this is the total area of the product rectangle, and then you subtract this original rectangle. Right, the product rectangle is this entire rectangle here, right? And the original rectangle is this white rectangle here. So again, this one here is the product rectangle, which is the total rectangle. And then this one here is the original rectangle, which is the smaller one. If I take the difference of these 2 areas, I simply take the sum of these 3 areas here. Now, the way he's breaking this up here is the difference between this white rectangle and the total rectangle is the top strip plus this side strip. This top strip is u of x plus h times delta v. As I mentioned, delta v is v of x plus h minus v of x. This side strip is, the height is v of x, the width is delta u. Delta u is u of x plus h minus u of x. So if you have this picture in mind, you can kind of see where the 2 terms in the product rule comes from. It comes from these 2 long rectangles. If you take this limit as x goes to 0, as h goes to 0, well, u of x plus h just turns into u of x. Sorry, I should divide by h first. If I divide this by h, then here you'll get the derivative of u times v, and then here you get your u times v prime plus v times u prime. All right? Right. Now what about reciprocal rule? Well, reciprocal rule starts just from the product rule. Right? We can use this expression, v times 1 over v equals 1. Then we use product rule on the left-hand side. You're going to get two terms. You get the first times the derivative of the second, plus the second times the derivative of the first. Okay? First times derivative of second is v times derivative of 1 over v. Now, I don't know the derivative of 1 over v, but I can use this expression to solve for that derivative. Okay, so that's first times derivative of second. This one is second times derivative of first. Second is 1 over v. Derivative of first is dv dx. All right? So I can solve for d dx of 1 over v. I isolate that on one side, and I get this expression here. It's minus dv dx divided by v squared. All right, so that's how you get the product, the quotient rule, the reciprocal rule. Again, the quotient rule, you would just take the derivative of u times 1 over v. And you use the product rule on that, and you will get the quotient rule. Now, for me, I always forget which is the minus sign. There's one that's a minus sign, and there's one that's a plus sign. If you remember that the minus sign goes with the derivative of the bottom, right? Because that's what comes from the quotient rule. So the derivative of the bottom has the minus sign. The derivative of the top doesn't have the minus sign. So there you got your quotient rule. All right? All right. Then we've got the power rule, and he shows this box for 3 dimensions. This is kind of like the 2-dimensional one, only you do it with a box. Now you could do it in n dimensions, but that would be difficult to add. But here you can see that you have a lot of, if I take this small, it's a rectangular box, and I subtract the big rectangular box, there's 1, 2, 3, 4, 5, 6, there's 7 pieces added, but there are 3 big pieces, these slabs. These slabs are much bigger than the other pieces, and you can actually neglect the other pieces compared to the big slabs. And those 3 big slabs give you your 3 terms. Remember, when you take a cube of something, when you take the derivative, you pull down the 3. Okay, so that's how that comes. Now, where does the du dx come from? Well, that comes when you build it up from 2, 3, 4, etc. If you use the product rule u of x times u of x, you will get a 2 u of x du dx. And then you just keep going on from there, and you can find this power rule. Now, this may remind you of the chain rule. In fact, this is a special case of the chain rule. Chain rule is really the most useful rule in calculus, but we don't do that in this chapter. All right, so that's my power rule. Here, this also interesting discussion where you have a fractional power, and he breaks it up like this. If u equals x to the p over q, then I can raise both sides to the qth power, and then take derivatives of both sides. On the left-hand side, we use the power rule that we just had, and then this one here is the polynomial rule that we know already. And then you just go ahead and solve for du dx, and then you substitute back in for u. Okay, and you get this formula here. Before, we really only proved this formula for integer values of n, but in fact the same formula works for fractional values of n. And it turns out that that extends also to any value of n, whether fractional, rational, or irrational. Okay. It's interesting, it also works for complex numbers, but we don't need to go there. All right, so here's our rules, and these are the rules that we're going to use to do the exercises. Next video, I'll look at some of the exercises.